Good afternoon, dear colleagues, dear guests. So we start our PhD defense of Hassan Butt with a thesis title, Carbon Nanotube Fibers as Embedded Electrons for the Dual-Stage Monitoring of Multifunctional Carbon Nanotube Nanocomposites. Supervisor is Professor Albert Nasibulin, co-supervisor Assistant Professor Dmitry Krasnikov. My name is Alexander Kvashnin. I am a chairman of this session. And let me start from the introduction of the jury members and the candidates. So first jury member is Professor Oleg Tolochko from the Peter the Great St. Petersburg Polytechnic University. So Professor Tolochko was born in the city of Khabarovsk, and in 1986 he received the specialty of an engineer metallurgist in metal science and the heat treatment of metals of the Leningrad Polytechnic Institute. In 1991 he obtained PhD degree from the Institute of Silicate Chemistry of Russian Academy of Sciences, and then obtained a Doctor of Technical Sciences in 1999. He has been working at the St. Petersburg Polytechnic University as a full professor and the head of the Material Science Department of St. Petersburg State Marine University. During his career, he has worked as a visiting scientist in KTH Royal Institute of Technology in Stockholm, in Stuttgart University, and the Korea Institute of Material Science. And currently he has an H-index of 21 and over 140 publications. Our next jury member is Professor Dmitry Lyubchenko from KTH Sweden. He received his bachelor, master, and PhD degrees in applied physics and mathematics from the Department of Physical and Quantum Electronics from Moscow Institute of Science and Technology. He has held various positions around the world with a number of institutes, including the Institute of Radio Engineering and Electronics of Russian Academy of Sciences, University of Liverpool, Helsinki University, or Aalto University in Finland, KTH Sweden, and other universities listed here on the slide. He was also a member of the EUMA General Assembly from 2016 to 2018, and his research interests include development of new materials for electromagnetic and optoelectronic applications. And currently he has an H-index of 20 with over than 200 publications. Next jury member is Dr. Pugang Ji. He from Hebei University of Technology, China. He completed his bachelor, master, and PhD degrees from Peter the Great St. Petersburg Polytechnic University in Russia, and he mainly specialized in the powder metallurgy and composite materials, and currently he is working in the School of Material Science and Engineering of the Hebei University of Technology in China, and also internationally in the Institute of Laser and Welding Technology of St. Petersburg State Marine Technical University in Russia. According to Scopus, he has an H-index of 16 with more than 65 publications, and currently he is specialized in the materials microstructure, mechanical properties, and applications of new materials. Dr. Yulia Ioni from Kurnakov Institute of General and Inorganic Chemistry of Russian Academy of Sciences. She graduated from the Lomonosov Moscow State Academy of Fine Chemical Technology in 2010 and received her PhD in 2013. And since 2009, she is an employee at the Kurnakov Institute of General and Inorganic Chemistry of Russian Academy of Sciences, and she is currently also a permanent researcher at the same institute, supervising the graphene oxide chemistry research group. She is also conducting research and teaching at the Russian Technology University Mireia. She has authored over than 30 publications and 3 patents devoted to graphene-related nanosized materials and has an H-index of 13. She has been active as a PI in 3 projects supported by Russian Foundation for Basic Research, Russian Science Foundation, and Ministry of Science and Higher Education of Russia, and also participated in various other funding projects. In 2013, she was awarded with a personal scholarship of Halda Topsu Foundation and was working there as a visiting scientist. Her research areas include fundamental approach to the tailored synthesis of graphene oxide and related composite materials, exploration of their properties, as well as their potential engineering applications. Next jury member is Professor Alexey Salimon from Skoltech. He is currently working in the group of hierarchically structured materials at the Center of Digital Engineering at Skoltech. He received a Candidate of Science degree from the Mises University in 1997. His H index is 21 with more than 115 publications. Professor Salimon has more than 20 years of experience in the field of new materials and technologies, including nanostructured metals and alloys, quasi-crystalline intermetallics, bulk metallic glasses, and others. Between 2002 and 2004, he developed the expert system for the funding of application for new materials under the leadership of Professor Ashby in INPG Grenoble. He also has a wide experience as equipment engineer in industries producing oil and gas equipment and related parts, listed here. Next jury member is Professor Alexey Yeshonok, who received his PhD degree in physics in 2007 and Doctor of Science in Biophysics in 2017 from Saratov State University in Russia. He worked as a postdoctoral researcher in Queen Mary University in United Kingdom and at the Max Planck Institute of Colloids and Interfaces in Germany, and also was a group leader at the Remote Control Theranostic System Lab Institute of Nanostructures and Biosystems in Saratov in Russia. He is the holder of the prestigious Alexander von Humboldt Foundation Scholarship of 2012. His scientific research interests include nanotechnology and nanobiotechnology, label-free molecule detection, Raman and surface-enhanced Raman spectroscopy and their applications. Currently, he is associate professor of the biophotonics group at the Skolkovo Institute of Science and Technology with an H index of 30 with over than 80 publications. So let me introduce the chairman myself. I'm Alexander Kvashnin. I completed my bachelor degree from the Siberian Federal University, then obtained master and PhD degrees from the Moscow Institute of Physics and Technology, and then habilitation from the Mises University here in Moscow. During my research career, I have held different visiting research positions in USA and Belgium. Also, I was a leader of Russian Science Foundation grants, Russian Foundation of Basic Research, and UMNIC program. I have authored 4 patents and has more than 70 publications with an H index of 30, and currently I am a full professor at the Project Center for Energy Transition and ESG here at Skoltech, and my research interests mainly include the computational prediction for physical properties of new materials, also the development of new methods for calculation of the properties using artificial intelligence and quantum chemical methods. Now let me introduce the supervisor, Professor Albert Nasibulin. He received his doctorate in physical chemistry in 1996 from Kemerovo State University and Doctor of Science at St. Petersburg State Technical University. Until December 2022, he was an adjunct professor at 2 departments in Aalto University, and he has held the post of research fellow in the Academy of Finland from 2006 to 2011, and currently he holds the position of professor of Russian Academy of Sciences since 2018. He specializes in the aerosol synthesis of nanomaterials, their growth dynamics and applications. He currently has over than 350 publications and 40 patents with an H index of 67. Currently, he is a full professor at the Center for Photonic Science and Engineering at Skoltech, where he has co-launched 3 startup companies. And let me introduce the co-supervisor of our candidate is Professor Dmitry Krasnikov, who has graduated from Novosibirsk State University in 2012 and received his doctorate in chemistry in 2016 from the Boreskov Institute of Catalysis. Since 2017, he has been working at the Laboratory of Nanomaterials in Skoltech. He is specialist in the field of physical chemistry, aerosol science, and catalysis. Currently, he has an H-index of 19 with more than 70 published works, 2 books, and 6 patents. His teaching experience covers the applied physics of aerosol science, catalysis, and chemical kinetics. He has been distinguished with various awards like the Alferov Award, Russian Federation President Stipend, and the European Council of Catalysis. Currently, he is an assistant professor at the Center for Photonic Science and Engineering at Skoltech, and his research interest includes nanoparticle synthesis and their various applications. And now let me introduce our PhD candidate, Hassan Ahmad Bhat. He has graduated with his degree in materials engineering in 2012 from the National University of Science and Technology in Pakistan, after which he worked for the industry in composite manufacturing for 2 years. Following this, he won a competitive full-ride master scholarship to the Chinese C9 Lick University Harbin Institute of Technology. He graduated in 2017 and joined Skoltech in 2018 as a research intern before switching to his PhD studies the same year. His currently research interests include carbon nanocomposites for functional and multifunctional properties. During his PhD, he has managed to accumulate an H-index of 6. Now you have about 40 minutes for your presentation. So the floor is yours. Please start.
Thank you very much to the chairman for the introduction. I will skip the first slide since it's already been covered. And we'll jump right into a little, all right. So as the title suggests, we deal with polymer nanocomposites, and I'm sure the committee is completely familiar with composite materials where you combine 2 or more physically or chemically different phases together to get a third phase, which has distinct properties. And in our case, since it's a nanocomposite and polymer in the name, we have one phase with nanoscale dimensions, and one is a polymer, which is our matrix. And when it comes to polymer nanocomposites, one of the most investigated is the addition of carbon nanotubes in various whatever characteristics, single wall, multi-wall, double wall, or different characteristics, however you want to look at it. And this is because, at least for the simplicity of this talk, when we disperse carbon nanotubes homogeneously throughout a matrix, we're able to make a percolation network. And this network imparts properties to the final composite. And the reason that it's multifunctional is because you are able to develop simultaneously all of these properties. So electrical conductivity, piezoresistive response, mechanical property alteration, thermal conductivity, frame retardancy. The list is quite large, but in our case, we will generally look at the electrical conductivity and the piezoresistive response. So coming to one of the main problems, polymer nanocomposites are generally slightly newer than traditional fiber reinforced composites. And like any material, they're able to develop defects at 2 main stages in their life cycle, one during the manufacturing and one during their application. Now, the techniques which were developed for material testing are usually either for manufacturing or for the application. They rely on expensive machinery. It's quite large at times as well. But most importantly, these techniques most of the time do not overlap, meaning that if you check or develop a system for one life cycle part, it doesn't work for the second. And embedded sensors have attempted to address this issue. Again, there is a cost issue when it comes to this. Most of the time there is a mechanical mismatch, and because you're putting something into a composite, it influences the volume and you get some defect induction at some points, which brings us to our hypothesis. We discussed in the beginning of my thesis with my supervisors, and we thought, maybe carbon nanotube fibers can give us an answer. Now, carbon nanotube fibers are assemblies of CNTs. They're assembled into a macrostructure, which is fiber-like, as you can see on the SEM images on the screen. But generally, they are porous. They have high electrical conductivity. And when it comes to polymer nanocomposites, this is a microstructure that is suitable for infiltration or interaction. And we thought, all right, let's see if we can use CNTFs to provide a material-based solution for monitoring both stages of CNT polymer nanocomposites without altering the mechanical properties. So this was the basic statement that we wanted to answer with our materials, which brings us to the research objectives and the questions which we wanted to answer. So first and foremost, of course, was the development of this technique with CNTFs, which allows dual stage monitoring, to understand if it does work, how is it working, why is it working, and to determine if the carbon nanotube fibers are actually sensitive to CNT type, their concentration, and some sub-questions come into these things, such as like, do the CNTF physical parameters affect the measurements, and is there a drawback for the mechanical properties if we go this route as compared to the rest? So to answer this, we came up with a semi-complicated structure of methodology. What we decided to do was have 4 things in our methodology. Of course, we needed to first and foremost develop our multifunctional nanocomposite matrices. So we decided to use multi-wall carbon nanotubes and single-wall carbon nanotubes. And we use a liquid molding process, in this case, half-open molds. And during this process, because we wanted dual-stage monitoring, we insert our carbon nanotube fibers into the gauge length of our material. And we do this so that we can monitor manufacturing parameters, understand if we can see any of the parameters that we want to see during the manufacturing process, leave them embedded here, and use them under mechanically applied load to see, okay, can we monitor how this material is behaving or changing when it's under loading? And just to show how these electrodes go into the length, into the volume of our gauge length, we just put some pictures up. Besides this, to answer the questions that we had before, we vary CNTF diameters to see if these parameters have any effect. We conduct measurements during manufacturing, monitoring by both 2 and 4 point, and then our mechanical loading was tensile and uniaxial cycle tensile tests, just to see where we get. So, of course, we wanted to use CNTs in this experimentation and dissertation. We use multi-wall carbon nanotubes and single-wall carbon nanotubes. For multi-wall, the aspect ratio is between 6 and 1,000, according to whatever dispersion we have from the manufacturer. For single-wall carbon nanotubes, is generally between 2 to 3,000, and the manufacturing method here is because we used master batches. We can go into this later as to why, but basically they are pre-dispersions which allow easier integration into further composite manufacturing. Now with single wall, for our carbon nanotube fiber production, we use single wall carbon nanotube thin films produced by our laboratory using the wet pulling technique. We will go into this. Of 2 diameters, we will also go into this. Again, for our nanocomposites, we use 0.25 and 0.75 weight percent. However, I have added the volume percentages for this so that one reviewer comment can be answered. I do not agree exactly with these calculations, but we can see this later, why. So, as we understood, we have our nanocomposites, we have these multifunctional property materials, and we want to monitor. But we need to integrate, so we needed 2 fabrication techniques, one for the nanocomposite itself and one for our carbon nanotube fibers. For the nanocomposite, we use master batches, weighed them to our required weight percentage, subjected them to pre-dispersion and ultrasonication for 30 minutes, followed by high-speed homogenization for about 1 hour. 45 minutes was about 7,500 RPM, and last 15 minutes at 10. Ultrasonication for another hour to help degas and disperse, degassing step, and then to molding. But before we went to molding, we fabricated our carbon nanotube fibers using the wet pulling technique as shown on the screen. And then the rest is as the methodology described before. Now, initially, as we started this in the very, very beginning of this experimentation, we had access to different types of carbon nanotubes, and we wanted to decide, all right, what form should we use just to see if there's any difference in our processing and everything, trying to get everything as optimized as possible. So we used different types, different carbon nanotubes with different bulk densities. And we made our nanocomposites with our manufacturing scheme, but as the screen shows, when we check the conductivity, which is related to the multifunctional properties later, we don't really see a major difference. There's no difference from the bulk density. But this, again, it's a small part of the thesis. And we also, because we altered the bulk density here, we wanted to do something with density with our fibers because it doesn't chemically alter them whatsoever. And we managed to increase our density. However, we saw that the microstructure was unfavorable afterwards. We removed the defects that would have been useful. And these both avenues were not pursued further in the thesis. So for our carbon nanotube fibers that were used, we used thin films of 2 widths to produce carbon nanotube fibers of 2 different diameter sets. One film width was 0.5 centimeters, one was 1. The thinner, let me say, less width film produced fibers which were of a smaller diameter, the higher width film for higher diameter. But the most important thing here was that we have a good difference, about 1.5 magnitude difference in electrical conductivity. So we can see this effect in measurements. We have a very big difference in diameter. So if there's anything related to our physical properties, we should be able to see the difference there as well. And everything seemed okay at this point. So we went back, we inserted both of these types of fibers from both these ranges into our molds. Added our nanocomposites. There were 2 types and 2 weight percentages of each. I come to the results of the monitoring for manufacturing now. Now, we did 2-point and 4-point. As I mentioned earlier, we used thicker fibers and thinner fibers. And the first image on your screen is from the thinner fibers. The second one is from thicker fibers. And as we can notice, the resistance during manufacturing is very, very similar. So if we just look at the diameter difference, it's quite large. It's about 3 to 7 times in cases. So we do not see any effect here. We see for our 0.25% by weight multi-wall carbon nanotube nanocomposite that we have a good resistivity range. It's in the range of what we see for literature. For our comparative, which I missed during the presentation, we compared our results to traditional electrode systems which are used. For metals, we used embedded copper wires and silver paste. So in this case, our metallic pairs, because we're using 2-point here and we changed the set for 4-point later, they show quite a bit of noise. They show quite a bit of magnitudinal difference as well. And when it comes to 4-point, which should remove this, which is contact resistance based, we managed to remove some noise, but still magnitudinal contact resistance remains. So this was our initial experimentation. And we see from here that, okay, our 4-point and 2-point measurements with carbon nanotube fibers, they're almost the same. We're in the same range. We see that the diameters do not have much of an effect. And we see that traditional electrode systems are not performing as good as we would like. So we continue this range of experimentation with a higher weight percentage. And again, we see the same typical type of behavior, higher magnitudes for the metallic embedded electrodes. We see higher noise as well during this whole curing process. But as soon as we switch to 4-point, for the metallic electrodes, this measurement errors are removed, but for our carbon nanotube fibers, we still have very stable results which match between the batches. Now, going over to our single wall carbon nanotube nanocomposites, the conductivity was much higher. Let me say it in this way, the resistance was much lower. And the behavior that we see between the diameter of the fibers for measurements and the 4-point and 2-point is again similar. We're seeing ranges which are almost absolutely the same in magnitude. There is a little variance, and I will go into this later when we come to it. But for our metallic electrodes, same basic response. But even here in this experimental batch, for our 4-point, we still see some spikes show up, just an artifact of this experimentation. So for our most conductive or least resistive nanocomposites, we again start to see similar behavior. So across the board, we see matching of our carbon nanotube fiber results. We see that our metallic electrodes are providing some form of contact resistance, either in the form of noise, either in the form of magnitudinal error. And our takeaway from this portion where we just monitor the manufacturing section is, okay, we see that they are sensitive to both types of carbon nanotubes in the nanocomposite. They're sensitive to different ranges of electrical properties, and they're stable throughout the batches. Now, once we molded our nanocomposites, because we wanted to use a one-step insertion process to monitor both post-manufacturing and during manufacturing. The first electrical property that we tested before was, of course, electrical resistivity. We had electrical data, and we take a look at these results. The horizontal lines are from 2-point. The vertical lines are from the thicker fibers in 2-point, and the solid lines are from our 4-point measurements. Now, for across the board, again, we see very similar results when it comes to our carbon nanotube fibers. Within variance, most of the cases, but in some cases, outside variance. And we have a limitation on equipment in this case, but again, this can be discussed in the discussion section. For the metallic materials, metallic embedded electrodes, we have a much higher reading. So like 1 to 2 magnitudes easily higher, a lot more variance. And our standard that we used for this was a conductor silver glue, which is used in multifunctional nanocomposites everywhere for contact creation. So our performance here is very, very similar to standards which are used right now. Silver glue or paste has the issue that with manufacturing, it's going to up your costs and it's not reusable. But in our case, with the carbon nanotube fibers, we do see these properties there. Now, of course, we needed to check another property, not just one. Electrical conductivity obviously is formed when there is a percolation network. And in our case, what we wanted to do is check if our carbon nanotube fibers are actually sensitive to any mechanical loading. We understand that the functional property does change of the nanocomposite. And in this case, we just wanted to see, is it going to be picked up by these embedded electrodes in the same way, or is there going to be some form of difference there? So we took our samples, which were molded according to ISO 527, ISO, and we tensile tested them. During tensile testing, we conducted simultaneous electrical measurements using our Keithley 2000 series DMM. We used a transverse head speed of 1 millimeter per minute. Again, one of the reviewers corrected me on this. I thank them for it. And we calculated a gauge factor. A gauge factor is basically the sensitivity of your material to a stimulus. In this case, it is tensile strain. So on the screen, I didn't put all of the tensile curves. They are in the additional size if we want to look at them, but I thought this one would be sufficient to basically describe the common behavior that we see. So as we apply stress, the material is again strained. We used our standard here, which we compared to, was pure epoxy without any embedded electrodes, so that we could understand if putting our electrodes into the material causes any premature mechanical failure. And for what we see, the metallic ones are slightly lower when it comes to UTS, which is ultimate tensile strength. We checked our UTS values, we checked our Young's modulus, we checked our Poisson's ratio, and we did the last two with the help of DIC. For the ultimate tensile strength, which is before plastic failure, we see that the metallic electrodes start to cause a significant loss in mechanical properties. And it's about 17% lower for this. As we move into our nanocomposites with an addition of carbon nanotube, addition of carbon nanotubes in the matrix, we start to see that, okay, the UTS of our nanocomposites with or without our carbon nanotube fibers is mostly similar. It is within each other's variance, but wherever we have our metallic embedded electrodes, we have a significant loss in this strength. Our materials start to fail sooner. Now, of course, we plotted on the next slide, I will come into the gauge factors, but our Young's modulus also begins to change, as well as the Poisson ratio. Now, for our pure epoxy, we have it in about 0.3 range. This indicates that we have a relatively stiff material, but with the addition of multi-wall carbon nanotubes and single-wall carbon nanotubes, we start to see a shift towards slightly rubbery viscoelastic plastic properties. For our single wall carbon nanotubes, which are 0.75%, we see complete loss in mechanical properties take place, which means that they are detrimental in the matrix to make these composites. They can give you some functional properties, but at the end of the day, you need to balance them. Our Young's modulus also started to drop, as we see, meaning that our stiffness was decreasing, and our gauge factor makes a good correlation with what we see in literature. For our more resistive composites, we have higher gauge factors. For our more conductive composites, we have lower gauge factors. Again, it goes to percolation network and how much it's changing during the application of strain. Now, coming to our piezo-resistive properties. For our multi-wall carbon nanotubes, we see a generally somewhat linear response. However, when we come to single-wall carbon nanotube composites, because we saw this shift in Poisson ratio, we saw this shift in Young's modulus, it's very bad performance mechanically. But again, here, this was how we plotted the piezo-resistive response, change in resistance, relative resistance against strain, and we come up with the values that we had. But one of the most interesting findings was that during our tensile mechanical testing, we noticed that wherever we had samples with embedded metallic electrodes, we had failure at point of electrode, at site of electrode, along the electrode. So wherever we had silver glue attached for making our contacts, as soon as the sample would fail, there would be a little shock force and they would detach. So this goes into saying that if you're going to use such contacts, there are problems with it. For our CU wire, which is image B on top, we start to see clean crack right there. And for CNTFs, if you notice, you'll be able to see in this region a little fuzzy places. Our contacts did come off, but a failure did not happen in this location. And just to help illustrate it, we have images from different types of samples for multi-wall, single-wall nanocomposites, and pure epoxy. In all cases, we see failure take place right there. So we understood, okay, there is a problem with traditional method when it comes to mechanical loading. However, we needed to check the cyclic response, and this was actually a decision that was come to with my IDC committee member, Professor Alexander Krasansky. The aim here, I would like to say, is not to understand the fatigue behavior, which is typical when you're doing cyclic testing. The aim was only to understand if our electrodes are going to pick up response the same way as the other systems during this process. So our carbon nanotube fibers, as we can see, are delta R is in the expected range of what we see for tensile. We see a good response. We see cycles generally between, in this case, for 5 to 700. For our surface applied, we see somewhat in the same range, but for our metallic ones, we start to see that failure slightly sooner. When we move to a higher weight percentage, this also becomes a bit visible here for the multi-wall carbon nanotube composites. And our surface applied ones are performing the best, of course. But the thing that we wanted to see only was, is our response there? Can we read it with these type of electrodes that we propose? And how do they perform against metallic, which was the most important? For our very conductive composites, we see, again, response is pretty much the same. However, we see some very interesting findings that the materials continued up to 1 million cycles. And that was quite a lot. That was unexpected. However, we need to understand that after coming to a decision about the testing conditions with Professor Ivan Sugecha from CMT, we decided that the stress level of 60% UTS is okay. And we used a R of 0.1 because compression did not work, and R of 0.1 just failed the samples completely. They were too stiff. So in this case, we need to understand that for the single wall carbon nanotube composites, because they showed a very, very low UTS, the force of testing here was pretty low as well. So that is one of the reasons why they sustain so many cycles. We see the same behavior for a higher weight percentage. However, we start to see a little gap appear between our reading times. This again is a limitation of the machine. We do not believe that it's very good at these low stress levels for testing, but we pick up the response. So that's what we wanted to see. Right, so we made our fibers, we see the effects of the diameter, we see the effects of sensitivity to different types of nano additions, and we needed to understand, okay, it's working, but why is it working? So we come to our microstructural analysis in this case. And what we did was first, obviously, we started with optical microscopy. So we took a single carbon nanotube fiber, we added a droplet of our nanocomposite matrix, and we noticed a couple of interesting findings. First, we were able to see that within the volume, there's a front moving. And it's interesting because we don't see this front on the surface. On the surface, our droplet stopped at this point. But when we looked at it with a little bit more contrast, a little bit more brightness, we could see, okay, it's moving. And then we took a look at the fiber and we see, okay, we have some defects in the volume. And this is the path that's being followed. So we also took a look at our traditional here metallic embedded electrodes, and we see that, okay, microcracks are present, but there's no real infiltration. There is inhomogeneous distribution, which we did not see along the length of this one, and there is separation. In some places, we also see just epoxy without any visible agglomeration or CNTs that we could discern from optical microscope. So of course, we needed to take a look at this in a bit more detail, and we went to SEM. On the screen are for multi-wall, lower weight percentage, higher, and lower is single wall for the same weight percentages. So we see our carbon nanotubes. We see that the percolation network here is a bit weaker. For our multi-wall at 0.75, the percolation network is a bit better. This is why we see the difference in electrical properties and the lower and higher piezoresistive response. For our single-wall carbon nanotubes, our structure is a bit different. They seem to be more flexible. The bundles are a bit more longer in length, and the structure is not circular as we see with our multi-wall carbon nanotube composites. At the higher weight percentage, very well-formed percolation network, good amount of connections over here, which gives us our higher electrical property and lower tensile piezoresistive response. But what was important for us was to understand how they're interacting. So we took a look at our metallic electrodes, and we see, this is from a fracture surface of one of the samples with multi-wall carbon nanotube composites. We see that there is no real strong adhesion. We see that, okay, microcracks are there, but we're not getting any type of infiltration. When we take a look at our matrices and our CNTs are present, we don't see any strong interaction between the two, which is probably why we see the magnitudinal and noise-based contact resistance there. In composites such as these, the percolation network is assumed to generally be the cause of all conductivity mechanisms. And some more images just to show this with our carbon nanotube fibers. We took it for metallic electrodes, and then we take it for our carbon nanotube fibers. In this case, if you look really closely, I hope you're able to see that we have a little bit of directional alignment. This is where our carbon nanotube fiber is. We zoom in and look at it a bit closer in a different place, and we're able to see, okay, our carbon nanotubes from our matrix are actually adhering to the surface. So we have a good connection, good adhesion, good wetting here, and we were lucky enough in another place to actually find these CNTs from the matrix actually connected to the CNTF. This may be with the epoxy, it may be mechanical interlocking. We're not able to tell in this exact place, but we also tried to remove a CNTF by tearing it slightly just to confirm this. And we see that all the CNTs which were in the matrix were adhering quite well to our carbon nanotube fiber. So again, some additional images just in case this was not clear. Our CNTF here, we have a lot of CNT bridging between the matrix. This is generally what the porosity looks like for our surface of the carbon nanotube fibers. So we understand, all right, On the surface, infiltration is taking place. In the defects, along these defects, we have flow going in. We increase the adhesion between the CNTs and the CNTF in our material, which brings me to our general conclusions. Overall, we see that CNTFs can be used as a single-step dual-stage monitoring electrode system for multifunctional property measurement of CNT nanocomposites. Our detection was similar for both multi-wall and single-wall carbon nanotube composites at different concentrations. So we see that we get a response from quite a wide range of electrical properties. Our gauge factors were between 2 to 12, which are quite good, very nice, relates to literature very cleanly. And so far, we did not see for our tensile properties any loss in mechanical properties. Our diameters really didn't seem to have an effect on this either. And our contact resistance was eliminated during both stages because of the enhanced interaction, infiltration of the matrix into the volume and the surface, and good connections in this case. So this brings me to the end of my presentation. There are some other slides, but we can go straight to questions and the discussion. I hope I was not too fast. I apologize to the committee. I'm a bit nervous.
Thank you for your presentation. Yeah, I think we can go to question and answer session. And in order to save some time, I think I suggest that we can ask questions, for example, one by one, starting from the, let's say, left-hand side, and then move on. So, Professor, your questions.
Thank you, Hasan, for your nice presentation. I have a few questions, and the first one regarding the slide number 11.
Oh, sorry, wrong button. Elena, may I have a little assistance? As you can see, I'm very nervous.
You have shown the conductivity curve for these pristine master batches and whatever samples. Yes. And in all samples, you have quite large resistance increase in this small fraction of the tubes in the samples.
Yes.
That meaning what you don't need too much to add and to have this.
Absolutely.
This quite, value of resistance. Can you explain how it's?
Yes, thank you very much for the question, Professor. It seems my presentation is also a bit nervous.
That's okay.
Oh, right here. Yeah. So we went with higher ones in this case. Of course, very low ones we can get percolation at. It's very possible to achieve this. However, if we notice that the spread is quite large, and this is because when you're near percolation, it's very difficult to control the development of the percolation network. At this case, you have ohmic contacts, you have tunneling contacts, but you cannot really control what the, let me say, distribution of both of them is. So we wanted to go, because we wanted to understand the mechanism of working, we wanted to see repeatability, we wanted to see all factors which are free of this variance. So we went with slightly higher weight percentages where our variance becomes much smaller. So at least we remove this to understand, is this from our different batches that we're processing? Because our equipment does have a limitation. We can't process a lot of volume at the same time. And we need to make samples in different batches. We use the same materials, the same processing method. But of course, there's always going to be variance between these. And we wanted to eliminate these factors, and we went with something higher in this case. Our selection of this weight percentage was, it's not extremely high for extremely high conductivity where we will see some piezo-resistive response, but enough to eliminate these variances of the manufacturing near percolation.
The second question may probably a technical one. When you perform this fiber by your method, when you pull out this film, can you control the thickness, the diameter, and how it depends on the thickness? Or,
very good question. So, scientifically, Yes, it's possible, but since it is a manual method, we do it by hand. The variables that we can eliminate are the length and the width of the film. The speed, we try and keep it the same as much as possible. We do have a device for this also, but it was not ready at that time. I do have some previous data. This technique actually was published by our laboratory 2019, I believe, and you can see quite a wide diameter variance in this. With the diameter variance, you have electrical property variance as well. We try and control it as best we can. We don't breathe when we pull it. We try and use the same volume of solvent on it. We try and adhere with the same amount of force. But of course, it is a manual method.
Thank you. And maybe last, this is slide number 22. When you have shown this, so the different set of the samples, and some of them, yeah, for example, the gray one,
yes.
So you have 3 samples,
yes.
I guess, yeah, and you have different these cycles, yeah. This meaning what you have, for example, first sample is destroyed, or what is happening here?
Yeah, okay,
why it's different? I mean,
thank you very much for the question, Professor. So in this case, generally with cyclic testing, let me just go over it quickly. We put our sample in a machine which oscillates in one axis. In this case, because we had relatively stiff samples, there was sharp breakage. So beyond this point, we have some electrical response, but we cancel it. We cancel it when we present the data simply because for our CNTF samples, we did not have breakage in this gauge length where our CNTFs were. For the metallics, we had exact crack there, and it was only fair that we don't show the whole cycle simply because it broke at this point, and we need to normalize it. We can still monitor the rest. We still have a reading because it didn't break here. Maybe we were unlucky in this, or maybe we were lucky. In either case, generally with cyclic testing, we have SN curves or graphs, sorry, where we plot the number of cycles and the stress. And you have your groups of data to formulate what exactly is the point of breakage. Data set is small. I won't say that this is exact confirmation that this is going to prove that the CNTFs last more cycles. At the exact point where our data ends, it's where we see sample fracture take place. And we stop it at that point. Perhaps they can last a bit longer, but it's not comparable.
Thank you.
Thank you, Professor.
Thank you. Professor Salimon, do you have questions?
Thank you. I have a few questions. First of all, slide number 7, I guess, or 8.
Slide 7 or 8.
Not actually, yeah.
Well, sorry, Professor.
Yeah, exactly. That's
there we go. There we go.
Okay.
Yes.
So the positioning of your CNT electrodes is somewhere in the middle of your samples.
Yes.
Yeah. So do you think any fatigue or any other events which happening at the surface can be detected through these?
That's a good question and very technical. So they are located there. And in our case, let me say it this way. We have our electrodes in this area of the volume. They do protrude to the other side. So as long as we have any surface defects, which do happen between these electrodes, we should be able to pick it up. We should be. Did we pick it up? There is a chance that we did. There is a chance that we didn't, simply because we are the first people who tried this. We don't really know from the cyclic curves what they represent. All we wanted to do at this point was to understand, are the electrodes actually going to pick it up? And then further on, what we're going to do is try and correlate this change in resistance to what type of defects. It's going to be pre-made defects, of course. There is a possibility, because I don't believe that it is, we assume, of course, that the piezoresistive response is uniform throughout this area that we're monitoring from the nanocomposite. However, the percolation network could be just better at the surface. So in this case, the response might be primarily from there or primarily from the volume, depending upon where it is. It's a technical question from the data that we have. I cannot tell you exactly. Do I think that theoretically it's possible? Yes.
Okay, but what are the underlying physical phenomenon of your sensitivity? Is it piezoresistivity only or percolation breakage? What is it?
Since we're operating at weight percentages which are much higher than just the percolation limit, we still describe it as a percolation network. It's just very well formed. So in this case, there are three things which may happen. One, your amount of ohmic connections can change. Second, your tunneling distance can increase because we're using, in this case, tensile strength. And in our third case, the entire network may deform. So for a very well-formed network here, like the weight percentages that we are using, this would be deformation of the network that we are picking up with our electrodes.
So, but actually, when you describe the health during this cycling, so do you believe that cycling may change percolation network, and how much, and in which way?
Very good question, very good question. For this, I'll go back to the graph slightly. So for our least resistive, our least conductive composites, we generally see a little variation start to take place. It's not exactly a complete baseline. For our metallics, we see this a lot more. And I assume here it should be because of some fatigue-based deformations which are taking place along the electrodes, at least in the areas where the electrodes are monitoring this material. For our very conductive composites, we don't see this, but again, the force here for testing was very low. What I would like to do to answer this question completely is to conduct a bigger set to give you a complete answer. Fatigue-based, it is somewhere inside this at some point. We see these dips, we see these spikes in resistance. We cannot at this point with this preliminary data, because we're the first people actually showing this, find out what is this related to. I would like to ideally have very thin samples, do this in SEM, to be able to understand, okay, the microstructure is changing at this point, our electrical resistance is changing at this point, this event or this fatigue type of mechanism causes this particular type of this. As far as it goes for structural health monitoring, it's a very broad term. There's fatigue, there's flexural, there's tensile, there's high speed impact, low speed impact. There are different types of it. Here, just to keep the thesis a bit narrow, a bit completable in the time frame that we had, we only focus on these tensile properties.
Okay, very last question. Did you try to make a Fourier transform of these fine structures? Because you know that every time you have a sort of noisy stuff.
Yes.
Yeah. Okay.
We haven't, but I understand where this question is coming from. If you'd like, we could perhaps later.
Okay. Well, usually people also try to couple these sort of measurements with acoustics.
Mm-hmm.
So not yet.
Not yet. Not at this point. First, we just needed to figure out if it works.
Yeah. Thank you.
Thank you very much.
Thank you. Okay, we can go next.
No, actually, some strange. You use metallic electrode, you use carbon nanotubes, some twisted electrode. But why don't you try just carbon fiber, just micro-sized carbon fiber, and what is not so good. Of course, there's no adhesion between the metal and epoxy if you get epoxy.
Right, very good question, Professor. Carbon fiber is also a conductive filament. It has been used in many cases, yes, and it has good mechanical properties as well. However, we are using commercial materials here. Commercially, carbon fiber, when it's produced, it is produced with a sizing, a layer of ceramic, let me say, powder, which is the best to protect it during transportation and shipping. To remove this sizing and this addition of polymer, you need to use some chemical techniques. And during the usage of these chemical techniques, there is a high chance, at least with people who do not have experience with it, such as myself, to damage the fibers in this case. So it really wouldn't be as good as I would have results for the metallics. This is exactly one of the things that we have noticed. It was raised by my IDC members as well, by Dr. Stanislav Ivlashin. We will continue with this in this direction, but first I need to understand how to remove the sizing properly.
I'm sorry for interrupting. This is a reminder to use microphones. Audience in Zoom can't hear us.
Sorry. Yeah. Okay, and the second one, in the case of metallic electrode, you buy it as copper. You just find anywhere just some copper wire and just decided, okay, it's a good electrode. No, did you try to make any surface treatment to make some functional group on the surface? Albert said, no, just Professor Nasibulin, he have a lot of experience in that.
Of course. Of course, your experience outranks mine by miles. I have no doubts about this. Generally, how it's done, we wanted to, again, it was the first time trying this. We wanted to have results which are comparable to materials which are published at least. So we wanted to see what's going to happen with wiring, which is typical for the usage with other types of sensors. This type of wire, this type of metal, either in the form of strips, either in the form of wires, in these cases, they are always inside the composite at some point. And this is where most publications do not focus because there starts to be a lack of mechanical properties in this case. So we wanted to be a bit straightforward. We wanted to understand like this is what it really is. This is how it's being used. These conductive contacts, either in the form of foils or films or wires, they are generally used in molds for one part or in the composites themselves for the other parts. And we wanted to not use a diameter which was too big. It would just be unscientific to do this. We wanted to match diameters which were close to our fiber diameter. So we were at about 100, 125 micron, which matches the values that we see.
Okay, and last one, because a lot of people, I'm sorry, I didn't pay attention before when I read the dissertation, but when you measured mechanical properties, the experimental error is so low, or 0.5 MPa, it's just, I think it's completely impossible. Just how many samples did you use and how it's...
Right. Mm-hmm. May I go back?
3 samples and just... in the table.
Yes, I'm trying to get there. 0.5. Oh, yes, this was only one. We got lucky here. This was complete luck. This is only one sample, one sample set, and we got lucky here.
Okay, thank you. Yeah,
you're completely right, because when I took these results to
it was not a question, it's a remark.
Okay, understood, Professor.
Thank you for your report. I remember your thesis and mentioned the impressive and easy to read text of your thesis. And you didn't present microscopy picture with different amounts of nanotubes. Why?
This is without electrodes, correct?
Mm-hmm. You have in your work many different types of samples, master batch, briquettes with different amounts of carbon nanotubes. And in your report, you didn't show it. Why? Have you a reason for it?
Yes, I wanted to make it a bit faster, to be honest, because in our case, we just wanted to demonstrate the microstructure. The actual extra images, I've been going back, I'm sorry. I added into the additional slides just in case someone wanted to see them. But our main purpose of showing those was to show, okay, this is the microstructure of this plain material. When we add our electrodes into it, are there any changes to A, the base microstructure, and B, what is the interaction? So going to these ones?
Yes.
Yes, so I kept them here on the side because our main focus of the thesis work was the interaction of the two materials. This provided some base background information for us to pursue further.
Thank you. And can you explain again why master batch is better than other forms of nanotubes?
Of course, of course. Here, it is more of a practical issue, not so much as a performance-based issue. Performance-based, we see that master batches, because they undergo a form of manufacturing with a matrix before, they are in some way predispersed. So they may have slightly better electrical performance in this case. However, the actual reason here was that powders are very aerosolizable. We did not want to use this in the laboratory. We wanted to use a commercial product, see how viable it is. And this is why we did this initial testing to match for performance. No difference in performance. Let us go with a safer material, which is less hazardous in this case. And it's also because we wanted a little hint of commercial materials to make this maybe industrially attractive in the future as we go more and we optimize this for these reasons.
Is it the master batch is cheaper than brick?
No. Master batch may be more, slightly more actually, not very much because the polymer is actually quite cheap. It's not much more expensive. As far as I remember, the powder from Oxial in this case, it cost, I think it was 15,000 rubles per gram, something of the sort. And the master batch is about the same price. It's about 17 or 18 when it comes to per gram. So we have about 40, 50 people in our laboratory who are working all the time. We want to avoid as much cross-contamination and safety issues as we can. And this is the reason. It wasn't much of a price difference. We see no difference in performance to multifunctional properties when we integrate this. So this was one of these experimental decisions. I generally, personally, do not like working with powders so much for this reason.
Okay, thank you.
Actually, I have a question, the same question with Professor Salimon, but let's talk about again. Let's go back to the page 8.
Page 8.
8. You did the test for or 2 points. In which direction?
In parallel to each other, yes.
Vertical pattern.
Yes, the electrodes are placed, let me say it like this. The electrodes are placed parallel to each other in the gauge length, which is at a right angle to the testing direction.
Okay. Okay, I have no question more.
Thank you for the question. I think this was my favorite one.
I also have the same question about the spectrum, which is very noisy, and about the Fourier. You can try to use the Fourier and then back and clean up the spectrum and see what you have, what kind of tendency it will be. And with what do you think? Why you have this noisy measurement? Is it due to device limitation, or is it not enough sensitivity?
Good question.
Because from your plots, it's very hard to understand what is the true resistivity you're measuring. You show the ratio.
Okay. So for the let us talk about one of these graphs. So in this case, we actually do have sensitivity. The only thing that makes us lose our sensitivity is the size of the magnitude. So the device automatically adjusts to some certain numbers according to the magnitude, which does in fact mean that, yes, it can be a little device issue. However, at our least conductive nanocomposites, we see we're at really the border with conductivity. So here I do expect some noise to be there itself, and it only looks a bit smaller because of the magnitude. I'm sure if we scale the magnitude, it might actually equal out. So it might not really be a sensitivity issue. Here, I believe it's more of a polymerization issue, but we don't look at this in this thesis. We have some other group who is doing that when it comes to curing. When we go to the 4-point, we're able to eliminate this. So 4-point, generally from our understanding, will only eliminate contact resistance.
Exactly. But
so
still sensitivity issue is
100%. I understand. We tried to. I would like I believe the device takes a sampling rate of 1 Hertz in this case for this particular type of testing that we had. I would like maybe slightly higher sensitivity, maybe try with a different device, different other things. But of course, this was preliminary proof of concept. I thank you for your idea. If you don't mind, I will try and use this in the future to try and get some better results and see if we can isolate these properties.
no more questions. No more questions.
Okay. If then there are no more questions, may I quickly say thank you to...
I think you will have time later.
Okay.
Yeah.
I apologize.
Yeah, as we already asked all the questions we have, so now the next procedure is you need to confirm whether you are satisfied with the revised version of the PhD thesis, as you have already reviewed them. So please tell whether you are satisfied or not with the corrections. Yeah, let's do it in the same order.
Yeah, I am satisfied. Yeah, thank you.
Well, I had 37 comments and remarks, so all of them were answered, so I'm satisfied.
Okay, I'm satisfied. Thank you.
I'm satisfied.
I'm also satisfied.
I also satisfied.
Okay, great. So yeah, now we can move to the words from the supervisor.
Thank you. You might have thought that Hassan did his work during like 4 years, but probably not many of you knows that in reality he spent only 1.5 years, because so he changed supervisor when he came to our laboratory. So we agreed that he will be working very efficiently, so to produce the PhD on a bit like slightly different topic, but it must be from the beginning to the end, like one story. So during these 1.5 years, so he has published like 4 papers, and which became the good basis for his dissertation. I'm very happy. So you were able to make it. So during 1.5 years, so I think that actually tells how hardworking Hassan is. He's extremely workable guy. So I'm very happy with this one. So he's always ready for new challenges. He's a very curious guy. So he's a hard worker, as I already told. But also, since our group constantly playing floorball, I cannot avoid mentioning so Hassan. You know, in our team we call him Pakistani gun, so which in Russian would be like Pakistanskaya pushka. Yeah, because his shots are very accurate, and he practically all the time he made goals. Yeah, so it's not only in science but also in games. He's a very efficient guy. Yeah. So I think he has grown as an independent scientist. He can work by himself, but he also supervised like a couple of guys already. And those two guys, he was like, he supervised, they wrote like papers. So that means that he is not only pushing them to write a PhD thesis, but they also write papers. So which is also a very good indication of Hassan. And I believe that all the jury members support me and so vote accordingly to award Hassan with a PhD degree. Yeah, thank you.
Thank you. And then let's move to the words from the co-supervisor.
Yeah, thank you, Mr. Chairman. So, well, first of all, I would like to say that Hassan is one of the most efficient and focused PhD students I have been blessed to work with, and like without any doubt. So actually, he's from, let's so to say, another mechanical side of material science. But in this 1.5 years, he showed the ability to quickly absorb all this chemistry inside of our group, all this knowledge of how to work, how to produce, integrate, and work with nanotube-based sensors. And this is, well, truly amazing. And he is very productive and always tries to fulfill the project until the very end, until the paper presentation patent, which is actually a pretty rare case for a PhD student or any other student. And well, yeah, he mentors, he already acts as a postdoc, he successfully mentors students, and this presentation is only a fraction of actual projects he is involved in, and he's without doubt a team player and can become a really good big scientist in the right, well, team. And all in all, for me, it is clear that he's like fully developed already to become a postdoc, and he has high qualification, and I'm only asking the pronounced jury to support his claim.
Thank you very much. So I think now we are ready for the closed discussion. So I think I would ask to leave the room everybody except jury members.
Just right? In case, shall we ask about the questions from audience, if any?
Okay, yeah, sorry, I forgot about
I don't see questions in Zoom.
There are no questions.
Yeah, so maybe...
Okay, maybe here in the audience somebody has the questions? No? Okay, then now you can leave the room and we will stay here for discussion. Okay, so our jury member committee concluded to accept your thesis as it is. So now, on behalf of the jury members, I can congratulate you with the awarding of PhD degree in material science and engineering. So, congratulations.
Well, wow, okay. So many people to thank because although this thesis might have been written by me, a lot of effort from a lot of different people went into this. It's not just a pure effort from myself. First, of course, my parents and my brother, my family, my wife, they put me on the right direction, kept me on the right direction, and put up with a lot of my moods and my ups and downs during this time. Of course, my supervisors, Professor Nasibuddin and Dimitri, without their trust, support, none of this was possible. I thank them very much for taking a chance on me. My jury members who gave me very useful comments for improving the thesis, but also for looking at it in a different way so that I understood it a bit better. Their questions really helped. My IDC committee members helped me throughout the time in Skoltech, put me, again, in positions where I needed to rethink things, to re-understand everything. And after all of this, it just helped me come to this point. Ups, downs, everything to here. And everyone in my laboratory, all the postdocs, all the professors, all the students, everyone, this journey has been a big one, and it's been very colorful because of all of your presence, and I thank you all for the time you spent with me. So thank you, everyone. Thank you to the committee. Thank you once again.